Okay, let's get started with lecture 25, the last lecture of the semester for the planets. All semester long, we've been discussing our solar system, the sun at the center, the planets, the other constituents of our solar system. We've talked about other stars and their planets. We've talked about the possibilities of life on other planets, around other stars. And we've even talked about our whole Milky Way galaxy of 200 billion stars. And indeed, we've mentioned several times that our universe as a whole contains hundreds of billions of galaxies, each one of which is something like our own Milky Way. Spiral arms for some of the galaxies, elliptical shapes for others, but a universe filled with galaxies that themselves consist of stars, most of which having planets orbiting them. But what we haven't addressed is the origin of everything. Where did this all come from? And how did the universe get to be the way it is? Why does it even have galaxies and stars within those galaxies? What is the internal composition, the structure of our universe as a whole? And how did it get to be that way? And by the way, where are we heading? So that's going to be the topic of today's lecture. Before I get into that, let me do a little business. There is a last homework due tomorrow. It's on chapter 24, the subject of the last two lectures on life in the universe, both the origin of life and life elsewhere in the universe. So the homework is due, as always, on Friday, that is tomorrow, at 6 p.m., And then there's this other even nastier issue of a final exam, and it will be December 18th. I think that's Thursday, December 18th, 11:30, right here in this room, 2 weeks from today. I'll remind you what the composition of the final will be. Multiple choice question, very much like the midterms. There will be an emphasis, as I mentioned last lecture, on the most recent 3 chapters, but the entire semester will be covered. And there will be an emphasis on the topics that were covered in the lectures and in the homework. So certainly the best way to study, in my view, is to go through all of the lectures, one lecture after the other, look at each of the slides in the lectures, try to understand each of the topics that you see on the slides, and if you're worried that you don't fully understand it, go back to the book, maybe look harder at the lecture, but use the lectures as the sort of focal point of the most important topics in the semester, and the homework problems serve in the same role. So use the lectures and the homeworks as sort of sparks to draw your attention to some part of the book where you can learn a little bit more about any topic that you feel like you'd like to brush up on. There will be a review session. It's not here. The review session, because this room is taken, is a week from today, but it will end at the same time as our class, 5 p.m., but it'll be in Valley Life Sciences Building 2050, which maybe some of you actually know that room. It's down the path from the Campanile. You go down about 2 minutes, and it's the big Life Sciences building on the right as you're heading west from the Campanile, and you walk in the big building there, and you'll find Valley Life Sciences 2050. The review session, of course, is not mandatory. Some of you may want to go. Some of you may not want to go. The GSIs will run the review session, and they're going to go through every important topic in the semester, one after the other, in the limited time, an hour and a half or 2 hours for the whole review session. and you'll be able to ask questions along the way. So there'll be a review of each chapter, chapter after chapter, and giving you a chance to first remind yourself of the important topics and to ask any questions that you have. And by the way, during the upcoming 2 weeks prior to the final, feel free to email me or the GSIs with any questions you have. I'm happy to answer any of them, and I know the GSIs will be as well. I'm going to be holding my office hours next week like I normally do, so you're welcome to come to my office hours. And even though discussion sections don't happen during RRR week, I'm sure you can meet with your GSIs whenever you'd like by emailing them and so on. So plenty of chances to get questions answered, even questions that don't have anything at all to do with the final exam. And indeed, that is the nature of today's lecture. Today's lecture is not going to be on the final exam at all. So you can sit back, relax, enjoy, critique the lecture, get melted into the universe as we take a trip through the universe, in particular, starting with the very beginning of the universe. Okay, so here we go on the last lecture. Something happened 13.8 billion years ago. We know it in time that precisely. 13.8 plus or minus 0.1 billion years ago, something happened. And we don't know exactly what, but we have a lot of evidence about the nature of it and the consequences of it. And what happened was an enormous explosion. Matter and energy all sprang forth, occupying the huge universe quickly, spreading out, condensing into galaxies. And indeed, it's the galaxies themselves that we see today that are the tracers of that explosion. They are still expanding away from each other, even today. So today, when we look at galaxies in the universe, we can measure their velocities, especially by the Doppler effect, and we see that all of the galaxies are moving away from each other. Think of the mass of a single galaxy. 100 billion stars and all the associated planets. The enormous amount of mass as a galaxy moves through the universe, and all the other galaxies with their masses moving through the universe. They have enormous momentum. They're all moving away from each other. And you can easily then run this movie backwards and ask, given where the galaxies are now and how fast they're moving away from each other now, where were those galaxies 1 million years ago, 1 billion years ago, 5 billion years ago? And when you run that movie backwards, obviously these massive galaxies were closer together. And another billion years before that, even closer still. What could stop them? And so all of the galaxies must have been extremely close together, and indeed maybe so close together that the compression, when you run the movie backwards, means that the galaxies disintegrated. They were composed of the constituent atoms and the energy and who knows what. And so physicists work very hard to figure out what must the universe have been like when the galaxies were all congealed together when you run the movie backwards. And it takes about 13.8 billion years for those galaxies to have all been squished together. And that essentially is where the age of the universe comes from. Taking the velocities of the galaxies now and asking when must they have all been on top of each other. And that's about 13.8 billion years ago. And just to put a little more emphasis on it, the galaxies today are still expanding away from each other. As you see here, space itself is expanding with the galaxies, and so you can easily recognize that this motion will continue and that it must have been a universe far more compact earlier on. This explosion is what we call the Big Bang. The nature of it, we have no idea. What happened before the Big Bang, we have no idea. We're not even sure whether the concept of space, never mind time, means anything prior to the Big Bang. So time and space, it appears, were created at the moment of the Big Bang, 13.8 billion years ago. The explosion obviously happened at a time when the universe must have been very dense, very hot due to that compression, over 1 trillion degrees. The universe has been expanding ever since, even to this day, and it will continue doing so. And as I'll describe in the second half of today's lecture, the universe is not only expanding, but it's accelerating in its expansion. It's actually expanding faster and faster and faster for reasons we have no idea. Science can't describe what happened before the Big Bang. It's a logical question for all of us to ask. Well, what happened before 13.8 billion years ago? But in fact, space and time aren't even defined prior to the Big Bang, so asking what happened before it is a question that defies actual physics as we know it. So the Big Bang clearly happened. There's a wide variety of evidence, not just the expansion of the galaxies, which is good enough, but there's a lot of other evidence of the Big Bang that comes from microwaves, infrared light, radio waves that were emitted at the time of the Big Bang that we're still receiving today. And I won't have much time to talk about all of that, a little bit, but not too much. But suffice to say, the Big Bang theory, as it's called, is an extraordinarily well-defended theory with lots of different types of observations that all point to a hot, dense explosion 13.8 billion years ago that created everything in this room, everything in our solar system, all of the galaxies, and all of the energy in the universe. Here's a depiction of it. I like this depiction because it has some of the physical properties that we actually measure in the Big Bang, and so that movie gives you a little sense of it. Let me run you through the history of the universe. What has been happening in our universe during the last 13.8 billion years? Well, again, running the movie backward, predicting the temperatures and densities at the first instance after the Big Bang, let's say the first millionth of a second or thousandth of a second, we can estimate temperatures. They were in the trillions of degrees. And at temperatures that high, protons and neutrons can't exist. And the reason is that they collide with each other and break apart into their constituent components. And you all know that protons and neutrons are made of quarks. And so, in fact, the universe that hot doesn't even have bound protons. They're broken up into their 3 quarks per proton and 3 quarks per neutron. There are also electrons, and there are photons, just like the photons that come from the lights here, but very much higher energy photons, because, again, in equilibrium, at trillions of degrees, the photons are extraordinarily energetic. So these are gamma rays. Yeah. Yeah, there are neutrinos. Definitely. Along with the electrons. Obviously, there can't be atoms because atoms consist in their nuclei of protons and neutrons, and there aren't any. So in the first thousandth of a second in the hot, dense universe, baby, infant universe, there are just quarks, electrons, and photons. As the universe expands in the first thousandth, the first 5,000ths of a second, the first 100th of a second, once the universe is a few tenths of a second old, it's cooling down and it is becoming less dense. As it cools, it finally reaches a mere billion degrees, a cool day in the early universe. And at about that temperature, protons are still colliding with each other, producing quarks. And to remind you, protons look like this nowadays, but they're made up of 2 up quarks and 1 down quark. And neutrons consist of 1 up quark and 2 down quarks to give them 0 charge. And the universe just has the innards of the protons and the neutrons. They haven't congealed together yet. Moreover, the particles, that is to say the quarks, can collide with each other and annihilate each other, destroy each other. And when they destroy each other, they turn into 2 photons. We've actually talked about this earlier in the semester when we talked about the nuclear reactions inside the sun. You may remember I said that an electron can collide with a positron. They annihilate each other to produce 2 gamma rays. And that kind of thing happens in the early universe with quarks. They collide, annihilate, and turn into photons. But it turns out that photons have enough energy via mc squared, Einstein's equation, that the photons can collide and turn back into quarks. So you have an equilibrium, kind of like a chemical reaction that goes both one way and the other way, reaching equilibrium between the quarks and these gamma rays, the photons. So the universe is very bright, but it's bright in light that consists of these high-energy photons, the gamma rays, short wavelength, high-frequency light, and they convert into matter very easily. Yeah.
So do we have an idea if there was antimatter?
So the question is, was there antimatter? Absolutely. Antimatter gets created as well, so there are anti-quarks, and so they're existing. Whenever I say a particle, all of the antiparticles exist too. And there was this is a subtle point, there was some asymmetry between the particles and the antiparticles, there being more particles than antiparticles. The particles and the antiparticles annihilated each other, destroying themselves, leaving us with the net leftover matter as opposed to antimatter. That's why our universe is regular matter and not equal parts antimatter. And no one knows why our universe had a little more matter than antimatter. Okay. Now, if you let the universe age, now this infant universe finally reaches a ripe old age of 3 minutes. It's cooled, it's less dense, so much so that the protons and the neutrons can form. And not only can they form, they can begin fusing together. This is a critical moment in the universe when not only have the protons and the neutrons congealed from the quarks, but the protons and the neutrons can react in nuclear reactions with each other. And of course, you know what reaction is likely to go first. The protons are going to combine to form helium, just as happens inside the sun and other stars. Fusion will occur. And so you not only form protons and neutrons from the quarks sticking together, but now the protons can react to produce helium. Now, at this point in the lecture, you might glance over at the periodic table. The Big Bang produced protons, which are the nuclei of hydrogen, and now through these nuclear reactions, protons and neutrons combine to produce the nuclei of helium. So you have a baby universe now with hydrogen and helium. And it turns out, although I won't mention it much, that there's yet one more reaction that can occur that produces lithium. So the early universe has hydrogen, helium, and some lithium, a teeny weeny bit of beryllium, it turns out, and that's it. There's very little else. The temperatures aren't high enough, the densities aren't high enough to produce any other elements by nuclear reactions. The whole universe, after 3 minutes into the age of the universe, has hydrogen, helium, a little bit of lithium, and that's it. That's the whole universe. Now, of course, some of the helium nuclei are torn apart by the collisions, but there's an equilibrium there too, and that equilibrium between the protons and the helium nuclei yields the final admixture of hydrogen and helium. And this can be calculated, and indeed, our universe today has a ratio of hydrogen to helium that agrees very well with the predicted amount of hydrogen and helium when you run the Big Bang forward in your computer simulations. So the 3-minute-year-old universe, a mere billion degrees now, has hydrogen and helium, and the fusion stops. All nuclear reactions stop, and the universe is done. It continues to expand, and we have 70% hydrogen, 25% helium, trace amounts, as I said, of lithium. There's a little deuterium. That's about it. Now, of course, this matter is still expanding away, and this crazy slide that I've just put up is sort of a circus depiction of our universe. Let me walk you through the circus. On the left is the Big Bang, and time proceeds from left to right, time increasing. Here's 10 to the minus 6 seconds, a millionth of a second. And that's where the quarks are. There's some quarks. At 3 minutes, you have protons making hydrogen, fusing with neutrons into helium. So after 3 minutes, you've got some bona fide regular atoms. And then as time goes on, other things happen. Like, for example, this is a key moment. When the universe was 300,000 years old, still you might say an adolescent, the universe enjoyed this thing. The protons combined with the electrons to make a bona fide hydrogen atom with a proton in the nucleus and an electron orbiting around that proton. So you have a real live, complete hydrogen atom. So that's what happens after 300,000 years. And you see, by the way, the universe had cooled down to a mere 10,000 degrees Celsius. Quite a lovely, tepid temperature. A little more than a cup of hot tea, though. And then after 1 billion years, something miraculous almost happened, but it's not a miracle. The atoms were gravitationally attracted to each other. Now here I just lied. Let me tell you my lie. Not only are there atoms in the early universe, but there's another type of material that I haven't mentioned yet, and that is dark matter. A type of matter, the nature of which we have no idea. But I will tell you later in the lecture why we know the universe has lots of this mysterious, unidentified dark matter. It has gravity too, and so when I mentioned gravity, the gravity of the atoms toward each other and the gravity of the dark matter toward each other allowed galaxies to collect by their self-gravity clumps of material begin to form. And they form into giant clouds, of course, at first, because it's just hydrogen and helium. But those clouds collect and collapse into stars, and eventually the clumps of hydrogen and helium gas congeal into stars by this self-gravity. I'll have a movie that shows this in a minute. So starting about 1 billion years into the universe, we call that the beginning of the age of galaxies, because now you actually have nearly full-fledged galaxies. They are, in fact, infant galaxies. The first galaxies came into existence 1 billion years after the Big Bang, and this, if in fact, is the current era of our universe. We live in a universe that has hundreds of billions of galaxies. You've seen a picture like this. I've shown it many times. All you need to do is point any telescope on the ground or in space toward the night sky, and you see these congealed clumps of matter that we call galaxies, consisting, in fact, of billions of stars. Now, astronomers have synthesized the universe since the Big Bang using computers. You can simply program a computer to include the temperatures and the densities as the universe expands, let gravity congeal some of the matter, including the dark matter, and let galaxies form according to the computer, and see if the computer simulation yields galaxies with sizes, masses, separations from each other that agree with the observations. That's how you test a theory. You let the theory make predictions and ask, do the predictions agree with the observations? And I want to show you one of those computer simulations, and let me preface it by saying that in a computer simulation of the universe, if you just let the universe expand, all of the material would flow outside your field of view. So when we show the graphical result of the simulations, what we do is we take a chunk of the universe, like a cube, and we put ourselves in a frame of reference such that the cube expands with the expansion of the universe. This is a co-moving or co-expanding cube. So I'm going to show you a cube that you see right here that itself is going to be expanding with the universe, but I'm always going to show you that same cube, and you'll just have to keep in mind that the cube itself is expanding, as is all of space, as the universe expands. So here's how it goes. There's the early universe with a uniform smear of matter. Gravity brings the atoms closer and closer together, and the dark matter. And as gravity brings the material closer together, it clumps into filaments, collections of matter, even small clumps that themselves are galaxies. I'll show you the movie again. This shows the whole history of the universe up to the present. A smear of material, gravity clumping the material together, and finally galaxies forming as we see them today. And for those of you who want a little spice of professional astrophysics, this parameter z is, I hate to do this to you, it's something called the redshift. So the universe has an average size to it. As it expands, the size gets bigger and bigger. And z is a quantity that represents the redshift, which is very close, a close cousin of the doppler shift of the light from the galaxies as they expand away from us. So at the present time, galaxies nearby have no redshift at all. So, okay. So now you've seen the whole history of the universe. What does it look like today? This. There's our universe. It expanded quickly, it inflated actually, and it's still expanding today. The galaxies are all moving away from each other. There are spirals. There are elliptical galaxies, there are irregular galaxies. This is a foreground star in our own galaxy, but everything else you see here, this is a Hubble Space Telescope image. Every other speck of light you see there is a galaxy of 100 billion stars or so. Now, I want to take a little diversion for 5 or 6 minutes in today's lecture from talking about the whole universe to talking about something very, very important that happened within the galaxies, something we haven't discussed at all in this class. And that is that the galaxies now consist of stars. Stars are burning hydrogen in their centers, converting the hydrogen into helium. And when they get done burning hydrogen into helium, they're out of hydrogen. Now they only have helium. They burn the helium in nuclear reactions, converting it into some of the other elements, notably carbon and oxygen and even sulfur. Then the stars burn up all of their helium, and eventually they run out of successive fuels, leaving a dead star with no nuclear fuels left at all. And here's what such a star looks like. The hydrogen is long gone in the center, having burned into helium. The helium burned into carbon and oxygen. The oxygen burned into, essentially, iron in the end. And so you see the debris, the daughter products of the nuclear reactions, left over like coals in a fireplace. These are the leftover nuclei, the iron atoms, from all of the past nuclear reactions. And then there's a succession of shells where material was burned into heavier elements up the periodic table here, up into heavier elements, and then in the outskirts of the star is still the hydrogen. It never burned because it never got hot enough and dense enough for the hydrogen to burn. So in the outer onion skin of the star, you still see the original chemical composition of the star, hydrogen and helium. There's an inner shell where some hydrogen burned, so all you have is helium, and so on. So the most massive stars, especially stars that are 5 or 10 times the mass of our sun, die over billions of years by virtue of having extinguished all of their nuclear fuel, leaving an onion shell structure of the debris, the leftovers from those nuclear reactions. This star cannot support itself anymore mechanically against its own self-gravity, so it collapses. These massive stars suffer a terrible fate after the iron can't burn, as I say here. No nuclear reactions can occur. There's therefore no energy production occurs. Gravity overwhelms the star, the self-gravity, and the star has no choice but to collapse. It collapses in on itself. Some amazing physics happens at that point that produces neutrinos, gamma rays, and for reasons that astronomers do not yet really understand, at that point, some energetic particles are created that cause the star to explode. And these stars, after collapsing violently, then proceed to explode violently in what is called a supernova. A core collapse supernova, the core of this massive star, as you see, is imploding, but some kind of nuclear reactions occur due to that implosion, again, the nature of which we don't fully understand, that causes this dead, dying star to explode. And we know this because we observe them all the time. Here's one such explosion. This is a supernova explosion called the Crab Nebula. You can see the gases are still expanding away from each other. There was obviously an explosion toward the center. People saw the explosion. Both Chinese astronomers and European astronomers in the year 1054 saw this incredibly bright star in the constellation Taurus. It appeared, and then a few months later vanished. And that star, now gone, left behind this so-called Crab Nebula, which is the debris, the gases from that exploding star. The explosion, of course, was very violent. It brought the temperature of the gases to billions of degrees, and these supernova explosions then have interiors with high temperature, high density, and therefore nuclear reactions can take place, indeed building up virtually all of the elements in the periodic table. The supernova explosions are so hot and dense that even the carbon, nitrogen, and oxygen and sulfur that got produced from some of the earlier reactions can fuse together to make all of the elements you see here. And I could tell you all about the nuclear reactions that lead up to them, but suffice it to say, and you can imagine this, a whole network of nuclear reactions occurs that produces all of the elements in the periodic table, up to 92. Where's 92? I can't find it. There it is, uranium. All of the naturally occurring atoms in the universe are produced in these supernova explosions. To be fair, there are other stars that can do a little nuclear reactions as well, contributing to the heavy elements in the periodic table, but it's certainly the supernova explosions that produce the vast majority of the atoms that we enjoy in our universe today. It's an amazing reality. I'll show you some pictures of other supernovae. Here's a gorgeous one. There's another one. There's another one. These are the remnants, the debris of the supernova explosions observed in our own galaxy. Here's a supernova that went off in a neighboring galaxy. Isn't that exquisite? Went off in the Magellanic Cloud, a nearby galaxy. Here's another supernova explosion. And to summarize, these violent, energetic explosions of stars allow nucleosynthesis to occur, i.e., producing the nuclei of all of the elements in the periodic table. The 92 elements up to uranium were all constructed in the centers of stars. Except for hydrogen and helium and a little lithium, as I mentioned, the hydrogen and the helium came from the Big Bang. So did some of the lithium, but all the rest of the atoms of which your human body is composed, the Earth is composed, the Sun is composed, all of those atoms came from supernova explosions. So think about that for a minute. The atoms of your body were at one time in the center of an exploding star. Your body is made of atoms that were in a star at some point a few billions of years ago. Otherwise, you wouldn't be here. Creepy. You are made of the debris of a supernova explosion. Now, I'm going to change topics slightly because while the first half of today's lecture was interesting, important perhaps, now I'd like to talk in the last 20 minutes about the nature of our universe that we don't understand at all. It's an embarrassment, and I'm going to tell you how embarrassed we astronomers are, because there's not just the bright, lit-up side to our universe with photons and atoms. There's a dark side to our universe, and it turns out the dark side of our universe is most of it. Here's a pie chart showing what our universe is made of. There is ordinary matter. Those are the atoms we've been talking about the last 30 minutes. All of the atoms in the periodic table that the chemists and the physicists and the biologists are engaged in. They're dealing with ordinary atoms that combine into molecules. That's ordinary matter. But our universe as a whole consists of two other types of material, for sure. Dark matter, which is some kind of material, the identity of which we have no idea, and the light from which we've never detected. We have detected its gravity, and I'll talk about that in a second. And even more profoundly, our universe has a majority constituent called dark energy. Dark matter and dark energy. How could we possibly know about, let's say, the dark matter if we can't even see it, if we have no evidence of it? Well, we do have evidence of it, and here's what it is. Bear with me. It'll take me 2 or 3 minutes to bring you along on a very short story that I think you'll appreciate and you'll follow it. It'll take a little bit of cogitation. The idea is this. How do we know that there's dark matter? Well, the story starts with our sun and the planets. You all know that the planets around our sun, again with apologies, I'm heading toward describing our universe and the dark matter in it, but I'm taking an important digression to look at the orbital motion of the planets around our home sun. You could make a graph of the orbital speed of planets going around our sun in kilometers per second, 10 kilometers a second, 20 kilometers a second. How fast do planets go as a function of how far the planets are from the sun? 1 AU, like the Earth, 2 AUs, 3 AUs, 4 AUs, 5 AUs, like Jupiter. And you know, I think, that the planets close to the sun, like Mercury, go fast. And the planets farther from the sun go slower, like the Earth and Jupiter. You can make a graph. This is Newton's laws of physics that you could derive yourself. The farther a planet is from the sun, the slower it goes. Venus, there's Mars, and so on. This follows from Newton's laws. If you wanted, you could derive this curve that you see here, orbital speed versus distance. And here's the answer you would get, that the velocity of a planet in its orbit, the speed of a planet in its orbit, is equal to the square root of the gravitational constant times the mass of our sun divided by the distance, all under the square root sign. Don't worry about the equation, nobody cares, but there is an equation that relates the velocity of a planet to how far away it is, the distance, and there's the distance on this graph, and there's the orbital speed on this graph, and there's that fall off. Why does it fall? Why does the graph decline? Oh, because distance is in the denominator. The larger the distance, the larger the denominator. This whole ratio gets smaller and smaller with increasing distance. Fine. Objects orbiting a central mass, as they are farther from the host star, the central star, the speeds are slower and slower. That same law should hold true, therefore, for our Milky Way galaxy. Stars orbiting the center of our galaxy should move slower and slower as you consider stars farther and farther from the center of our Milky Way galaxy, or any other galaxy. And about 30 years ago, when astronomers started making these measurements, they were sure they would see this decline, but they didn't. Here's the same graph orbital speed of the stars in a galaxy, these are galaxies now, the orbital speed of the stars in a galaxy as a function of how far the stars are from the center of the galaxy. That's like the sun in our solar system, but now we've translated this to a galaxy. Farther from the center of the galaxy, you would expect the orbital speed would get slower and slower and slower. That isn't what happened. Very famous astronomer discovered this in the late 70s and mid 80s. Her name was Vera Rubin. And when she reported her results, her observations, people thought, this can't be. We know that the farther a star is from the center of a galaxy, the stars should be orbiting slower and slower. So she went back and she did another galaxy and another galaxy, and all of them showed this same effect. And she is now credited correctly with demonstrating that galaxies must have extra mass here to compensate for the fact that the distance is increasing. Stars farther from the center should move more slowly, but they don't, so there must be more mass. And the more mass must exist farther and farther from the center to account for the stars moving slower, or should have moved slower and slower, but they don't move slower and slower. They have a constant velocity, as you can see. So Vera Rubin discovered dark matter. And we now call it dark matter because clearly there's some kind of mass that exists within a galaxy that we can't see. It's not stars, it's not gas, it's not any other kind of atoms. There's other evidence that came in the last 10 or 20 years for dark matter. I'll only mention one or two. One of them is really exciting. Light bends gravitationally when it passes by a galaxy. So here's a light source. It might be a distant star or a distant galaxy. And when that light goes by another galaxy, the light bends due to the gravity of the galaxy into our telescopes. We can analyze that bending of light, as shown here. Light bending by a galaxy, there's the bending, and analyze it at our telescopes. And again, we infer the existence of enormous amounts of unseen matter, some kind of matter that acts gravitationally, not just on the stars, but on the light. So clearly there's dark matter. And there are many other ways to see dark matter. I'm going to show you a couple. These are galaxies that obviously have, and this is complicated, a foreground massive object that distorts the light from that galaxy. You see the light is distorted. It's spread out into wisps and curlicues and arcs. You see the arcs of blue light? Some of them are almost full circles. The galaxies have mass in them, not just from stars, but from dark matter, bending starlight into these arcs. People analyze them. I won't go into all the details. Sometimes you see multiple background galaxies, all being different images of a background galaxy. And sometimes there are places in the night sky where the mass of dark matter is so great that the foreground galaxies, the galaxies near us, are bent and distorted like crazy. And actually, these are galaxies that have been stretched. Their light has been stretched out into arcs, as you can see. There's many of them, due to dark matter in between us and the galaxy. And people analyze this to measure the amount of dark matter. The bottom line is, when you estimate and measure how much dark matter there is, there's more of it than regular atoms, regular matter. So all the matter that we know and love that sits here on the periodic table, that's the tip of the iceberg. The dark matter in our universe dominates by a factor of 5 or 10. What could that dark matter be? Long story short, people have worked very, very hard on this question, and nobody knows what the dark matter is. You might think it's free-floating planets out there that are pretty dark. No, there would never be enough mass in the form of planets. There aren't enough Earths or Jupiters to account for the enormous amount of mass. It's way more than even the amount of mass in stars. So forget that. What about a universe filled with black holes? Well, no, because if there were lots of black holes, we would see the bending of starlight around the black holes in very localized regions. We don't see that. There's no way there could be so many massive stars that led to the black holes. So there's a lot of reasons to rule out black holes. Our universe isn't filled with an ocean of black holes out there. So what could the dark matter be? Well, most people agree, who study this problem hard, and I'm not one of them, that there's some type of elementary particle that was created in the Big Bang. Some kind of particle that was created along with the quarks and the electrons and the photons that we know about, but some other particle was also created that doesn't emit any light at all and doesn't interact with atoms or light very well. Some kind of elementary particle that's yet to be discovered. Floating through this room, floating through our solar system, floating through our galaxy and the whole universe, some kind of particle by the trillions and trillions and trillions that pervades the entire universe. And it clumps gravitationally to help form the galaxies. So that's dark matter. And there's about a factor of 10 times more dark matter than there is ordinary matter. Not quite a factor of 10. And that leads to the last topic of today's lecture and the last topic of the semester. And that is dark energy. Not dark matter, but dark energy. Dark energy was inferred to exist and now is inferred to exist from a wide variety of observations, but the first real inkling of it that convinced everybody came from watching these, the supernova explosions again. I brought them up a few minutes ago, describing how supernovae explosions produce all of the elements in the periodic table. But now I'm going to invoke supernova explosions in a totally different context, and that is as lampposts. When a supernova goes off, we've studied them so carefully, astronomers have, that we know how intrinsically luminous they are. We know how many watts, like a light bulb, they are. And long story short, by calibrating their wattage, you can then make an observation of a supernova and measure its apparent brightness. How bright does the supernova appear to be? And knowing how intrinsically bright it is, and then measuring how apparently bright it is, you can determine the distance, right? A light bulb has a certain brightness, 100-watt light bulb, but if you put that light bulb far away, it's much dimmer. And by measuring how dim the light bulb is, you can immediately determine how far away that light bulb must be to be as dim as it is. And that's what astronomers do. They watch galaxies. Here below is a galaxy minding its own business, happy. But there's a dot that appeared out of nowhere and lasted for a few months. That's a supernova explosion in that galaxy, just outside the galaxy. Here's another galaxy minding its own business, and right there is a supernova explosion. Here's another galaxy, there's the supernova. Another galaxy, there's the supernova. Another one, there's the supernova. Sometimes the supernova explosions are so luminous, they are as bright as the entire galaxy that they live in. Amazing. And the key behind these supernovae is that they are standard candles. We know the wattage. And so as a result of knowing the wattage, we can tell how far away the galaxies are, as depicted with these light bulbs on the left. But here with galaxies and their supernova explosions, we can figure out the distance to the supernova from measuring its apparent brightness, because we've calibrated their intrinsic luminosity. And there's a special kind of supernova, for those of you who want to be experts, they're called type 1a supernova explosions. Those are the golden ones. They're the ones the easiest to calibrate. And you analyze the brightness. We call the brightness a light curve. We measure this doppler shift, or sometimes called the red shift, of the supernova light. And most of this work was done right here at Berkeley. Two different astronomers played leading roles. Saul Perlmutter is a member of the physics and astronomy departments here at Berkeley, and also the Lawrence Berkeley Lab. Saul and his team measured the brightnesses of supernova explosions, measured the Doppler shift of the supernova explosions, telling us how fast they're moving away and how far they were from us. There was another team that did similar work, and one of our professors here, Alex Filipenko, was on that team. So we had two different faculty members here at Berkeley that played key roles in measuring the expansion of the universe by using the supernova explosions as markers, as buoys on the cosmic sea of expansion. This work was given the Nobel Prize 2 years ago. What they found by monitoring the distances to these supernovae, as I mentioned, and the velocities of the supernovae by using the Doppler effect, they found that the universe was expanding at an accelerated rate. Here's the point here. The universe has galaxies that are flying apart at ever-increasing speeds. Somehow or other, the galaxies and their supernovae are not only expanding away from each other, but the galaxies are going faster and faster and faster in their expansion. Nobody expected this, but so that's why it was quite a shock and warranted the Nobel Prize. Why is it that the galaxies are not just flying away from each other, but accelerating in that expansion? Nobody has the slightest clue. I mean, no idea. We're so clueless that we gave it a name so that people think we're smart, dark energy. But I promise you, the term dark energy that you'll hear for the rest of your lives is a made-up word. It's what you do in science when you don't fully understand, or maybe not understand at all what's going on. You categorize it, give it a name, but we don't have any understanding at all of what dark energy is. It's the stuff that causes the universe to accelerate in its expansion. This is a graph that's too complicated, so I apologize. But it's a graph, you can't even read the axes. It just shows how fast the universe is expanding as a function of distance, essentially. And you can see that the universe is expanding at a rate that people can measure, and that's what gives us a measure of how much dark energy there is that's causing this expansion. And the bottom line is shown here. I've shown this slide already earlier in the lecture, but now we can understand it a little better. This is what our universe is made of. Here's the ordinary atoms and molecules. The Earth, the Sun, other stars, galaxies are made of ordinary atoms and molecules. 4.9% of our universe is made of the stuff that we've been studying all semester long. It's a sad statement that I've tricked you all semester. We've been studying the tip of the iceberg, and we left out the iceberg. And by the way, that's what's happening in all of your other classes here at Berkeley, too. If you take a class in history, you're only studying the ordinary matter. If you're taking a class in psychology, well, brains are made of ordinary matter. So we're so ignorant about our universe, we have no choice but to study this little shred of what our universe is made of. But most of it's made of dark matter, and dark energy, 27% and 68% respectively. There's other evidence of dark energy, and I'll just mention one more that's so exciting because it was in the news yesterday or the day before. Back in the 60s, some radio technicians working for Bell Laboratories were studying how to make a better radio transmissions. They built a big radio receiver, these two guys here, and they were bugged by noise, constantly getting radio noise in their transmissions. Turned out it wasn't noise at all. It was radio waves coming from the Big Bang. And it's been very well studied to this day. Not only that, but the amount of light coming in this radio emission follows the thermal emission curve that you've seen way back earlier in the semester. The amount of light as a function of wavelength, a nice thermal emission curve. The universe is warm. And it's warm because the Big Bang was so hot earlier on. It's cooled off since then, but it's still warm. And you can measure that emission. And so what people do is they use radio waves and so-called microwaves. And here's a picture of the universe showing those microwaves, what the universe would look like if you could detect the microwaves. That's only a bit of the story. What's really interesting is if you subtract the average brightness of the universe away, this green that you see, if you subtract the average radio waves away, here's what's left over as the bumps, the extra bright and the not so bright spots. This map was just produced in the last week. It's a baby picture of our galaxy, of our universe, a baby picture of our universe made with a satellite in space called the Planck satellite. And you see some parts of our universe early on, where these radio waves come from, are a little hotter than average or a little cooler than average. And that structure of the baby universe is what eventually congealed into galaxies and stars and planets and your human body. If the universe had been perfectly uniform, like milk spilled on the floor, it would never have had the possibility of congealing into little pockets one place or another. Why would it? But instead, the baby universe actually does have regions of higher density, higher temperature, lower density, lower temperature. And so this baby picture of the universe offers enormous support for the whole model of dark matter, dark energy, and a little bit of ordinary atomic matter. So this pie chart for the universe is dramatically supported by those baby pictures of the radio waves from the Big Bang. And what's really, I think, profound and dramatic is that we live our whole lives just trapped, if you will, in the ordinary matter. But boy, is it a beautiful patch of ordinary matter. It all came from supernova explosions, except the hydrogen and helium that came from the Big Bang. And it's rather lovely to see that we humans, composed of star stuff, in a way are kin. We are cousins of the supernova explosions. We're cousins of the stars that died and left debris for us to be born. And we are also a part of the expanding, accelerating universe as a whole. So I will stop there. Thank you very much, and good luck on the final exam.